All right, so we are now looking at a hydrohalogenation. So we'll think back about that name of the reaction after we figure out what happens here. But I think that we can use our two rules of organic chemistry. Remember, our two rules are that negatives attack positives and the ball rolls downhill to figure out what the product is going to be in this reaction. First of all, where do we have negatives, where do we have positives in the reaction here? All right, so you should be pausing the video and writing partial positives, partial negatives in different places. Okay, you did that. Well, bromine is more electronegative than hydrogen, so we're going to have a partial negative over here, partial positive over here. And then you probably didn't write anything. I probably hope you didn't write any partial positive or partial negative over here. We don't really technically have a, partially, if anything, maybe the alkene is a little bit, the alkene carbons are a little bit partially negative because they are technically more electronegative than the carbons they're attached to. But what I really want us to refocus on is just remembering that when we saw an image of a pi bond, oh shoot, not on that page, earlier in the chapter, where was the electron density? And while we might not be able to draw a partial negative based on electronegativities, we did see this image, the electrostatic potential map that was computationally created, that shows that red region in between the pi bond, in between the atoms, is electron rich. So we do have an electron rich area right here. So I'll draw it in here. It's a partial minus right there. And that negative is going to attack the positive. So where is it going to attack? It's going to attack that hydrogen right there. So the first step of this mechanism would be that pi bond adding to that hydrogen. So what has to happen next in this mechanism? Is this enough for our first step? Can we draw the intermediates right here? What else do we have to draw? All right, hopefully you're thinking that, well, we can't add a bond to hydrogen without breaking a bond to hydrogen. It's just a valency rule, right? Hydrogen can only have one bond. So as soon as we're forming a bond to hydrogen, the hydrogen-bromine bond has to break as well. So that would mean that we are adding the hydrogen to one side of this alkene. Does the side matter? Well, let's think about that. Well, if we added the hydrogen to this side, we technically would have two hydrogens over here, one hydrogen over here, and a positive charge on that side. If we added it to the other side, we would have two hydrogens over here, one hydrogen here, and a positive on that side. Are these molecules different at all? No, they're identical molecules. It's just the same thing flipped over. So we don't have to draw both of them. We can just draw one of them. I'm just going to cross one out. It's not that it's a wrong one. It's just not necessary to have two. So that's one thing that is an intermediate here. And the other thing that's an intermediate is Br minus. So what's the next mechanistic step then? Negatives flow to positives, right? So this negative charge flows to the positive charge there. And our product added a hydrogen and a bromine to that pi bond. So thinking back to the name of this reaction, it's called a hydrohalogenation. Why is it called that? Well, we added a hydrogen and a bromine. So hydrogen and halogen was added. And in this process, we formed a secondary carbocation. So that's something to note. We'll see the type of carbocation being important in future reactions. So what about our reaction coordinate diagram? Will this be an exothermic reaction or an endothermic reaction? Okay, so we got rid of a pi bond. Are those strong bonds or weak bonds? We got rid of a pi bond, that's a weak bond, and we formed sigma bonds. Sigma bonds are strong bonds, so this should be an exothermic reaction. So reaction coordinate should be exothermic because we are forming stronger bonds. What kind of bonds are stronger? Pi bonds are stronger. So our starting materials might be right here, and our products might be down here. So what else do we have to have in this reaction coordinate diagram? Well, in this first step for our organic molecule, we broke a bond. We broke two bonds. We broke a pi bond and we broke a sigma bond, and we only formed a sigma bond, right? So we broke two bonds and only formed one bond. That must mean that, remember, it takes energy to break bonds, so we are going to a higher energy level. Our intermediates are up here, so these are our intermediates. I'll just put an I for that. So somehow we're going over an activation energy bump. We have our intermediates that are high energy. Another thing that makes them high energy is that our carbon doesn't have a full octet. Everything wants to have a full octet. We're missing it there. So we go up to our high energy intermediates, and then they will quickly, the slow activation energy barrier, go to the product formation. So in this reaction, carbon is our high energy intermediate, or the carbocation is our high energy intermediate. And that high energy intermediate is a secondary carbocation in this case. And a more stable carbocation will lead to a faster reaction. So if we could have formed a tertiary carbocation, that would have been a faster reaction than a secondary carbocation. What was the rate determining step here? This was the rate determining step, right? We know that it's going to be hard to break bonds and not form the same number of bonds that we broke, versus in the second step, all we're doing is forming a bond. That's going to happen fast, but when we're breaking bonds and not replacing those with other bonds, it's going to take a lot of energy to do that. That's going to make it our rate determining step. Yeah, so that's the general situation with how these hydrohalogenation addition reactions work.